Picture yourself on a tranquil hillside just before dawn, the horizon beginning to shift from darkness into an extraordinary display of color. The sky transforms into a canvas painted with deep oranges, radiant reds, and delicate pinks that seem to bleed across the atmosphere. This is a spectacle that unfolds every single day, one that billions of people witness, yet rarely pause to truly contemplate. The sunrise, beautiful, familiar, almost mundane in its regularity, is actually the final act in an epic journey that has spanned unimaginable distances and timescales. If we could trace the path of a single photon of light backward from where it enters your eye, we would embark on one of the most remarkable voyages in the cosmos. That particle of light has traveled through the Earth's atmosphere, dancing through layers of nitrogen and oxygen, scattering and refracting to create those magnificent colors. Before that, it crossed the vast emptiness of space, a void stretching 150 million kilometers, separating our fragile blue world from the massive sphere of incandescent plasma we call the Sun. But the journey doesn't end there. To truly understand where that photon originated, we must peer deeper still, through the turbulent and varied layers of our star itself. We must journey inward through zones of unimaginable temperature and pressure, through regions where matter behaves in ways that defy everyday experience, until we arrive at the very heart of the Sun, its core. Here, in a nuclear furnace that has been burning for 4.5 billion years, is where that photon began its existence. The Sun was born in what astronomers call a cosmic nursery, a vast cloud of gas and dust enriched by the remnants of ancient stars that had long since died in spectacular supernova explosions. From this stellar graveyard came the building blocks of our star, a glowing sphere of searing plasma that now dominates our sky and makes all life on Earth possible. The Sun is the product of complex physical forces that have played out over millennia, governed by the fundamental laws of gravity, thermodynamics, and nuclear physics. Yet despite its prominence in our lives, how much do we truly understand about this pivotal celestial body? What are the intricate processes that govern its colossal power output? What are its most breathtaking and dangerous features? And how are scientists managing to pierce through the blinding curtain of light to uncover the Sun's deepest mysteries? We're about to embark on a comprehensive exploration of our nearest star. We'll dive into its depths, traveling from the outermost wisps of its atmosphere all the way down to the fusion reactions in its core. We'll discover what secrets lie hidden behind that brilliant facade of light and heat, and we'll learn how the Sun influences not just our planet, but the entire solar system and beyond. Our investigation begins not at the center, but at the edge. Like savoring a piece of fruit by starting with the outer layers and working inward, we'll begin our exploration with the Sun's corona, the outermost layer of its atmosphere. This ethereal region extends millions of kilometers into space, creating a shimmering halo that can only be seen with special instruments or during the rare and spectacular event of a total solar eclipse. The corona is far more than just a pretty glow around the sunday. It's a dynamic and violent region where temperatures soar to millions of degrees, where magnetic fields twist and snap with the energy of millions of nuclear weapons, and where the solar wind begins its journey outward to fill the entire solar system with a stream of charged particles. Understanding the corona is crucial to understanding space weather, the phenomena that can disrupt satellites, power grids, and communications here on Earth. To study this hidden realm, scientists have deployed some of humanity's most sophisticated observatories. One of the most important is the Solar Dynamics Observatory, or SDO, a NASA space mission that was launched in February of 2010. The SDO orbits Earth at an altitude where it can maintain a constant watch on the Sun, capturing images and data 24 hours a day, 7 days a week. Its mission is elegantly simple, yet profoundly important: to better understand the solar variations that influence life on Earth and the technological systems we've come to depend upon. The SDO studies the Sun by observing it across multiple wavelengths of light, from visible light that our eyes can see to extreme ultraviolet radiation that would be completely invisible to us. By looking at the Sun in these different colors, scientists can pick out details that would otherwise remain hidden, revealing the complex structure and behavior of our star's atmosphere. Consider one particular image captured by the SDO using light at a wavelength of 19.3 nanometers. This is far beyond what the human eye can perceive, in a region of the electromagnetic spectrum called extreme ultraviolet. At this specific wavelength, which corresponds to a temperature of approximately 1 million degrees Kelvin, we can clearly see the higher regions of the sun's corona in exquisite detail. During a total solar eclipse, when the moon perfectly aligns between Earth and the sun, observers on the ground can witness the corona with their own eyes. For those brief, precious moments when the moon blocks out the brilliant photosphere, the sun's visible surface, the corona, becomes visible as a delicate, pearlescent glow extending outward from the darkened disk. It's a sight that has inspired awe and wonder throughout human history, one that has driven people to travel thousands of miles to stand in the moon's shadow for just a few fleeting minutes. But as breathtaking as the eclipse view may be, it pales in comparison to what the SDO can reveal. The spacecraft's instruments can see structures and details in the corona that are simply invisible to the naked eye, even during an eclipse. This makes it an invaluable tool for solar scientists who are working to unravel the mysteries of our star. Let's venture slightly deeper to features that exist just beneath the corona's outer reaches. By tuning to light at a wavelength corresponding to a temperature of 20 million degrees Kelvin, we can identify some of the most violent and energetic events in the solar system: solar flares. These are the intensely bright spots that appear in images of the sun, marking locations where enormous amounts of energy are being released in spectacular explosions. Solar flares are absolutely mesmerizing to watch, even in the time-lapse footage that compresses hours into seconds. They're simultaneously terrifying and hypnotic, representing the raw power of magnetic forces unleashed. These colossal explosions occur when the sun spews out immense amounts of electromagnetic radiation across virtually the entire spectrum, from radio waves to gamma rays, all in a matter of minutes or even seconds. The mechanism behind solar flares involves the sun's magnetic field, which is generated deep within the star by the churning motions of electrically conducting plasma. As the sun rotates, not as a solid body, but with its equator spinning faster than its poles, these magnetic fields become twisted and distorted. Imagine taking a rubber band and twisting it tighter and tighter. Eventually, something has to give. On the sun, when magnetic field lines cross, distort, and reorganize themselves rapidly in a process called magnetic reconnection, the stored energy is released explosively as a solar flare. The energy released in a major solar flare is almost incomprehensible. We're talking about events that release as much energy as millions of nuclear weapons, detonating simultaneously. To put this in perspective, the largest nuclear weapon ever tested by humanity, the Soviet Union's Tsar Bomba, released about 50 megatons of energy. A major solar flare can release energy equivalent to millions of such weapons, making even our most powerful technologies seem like toys by comparison. But solar flares aren't the only dramatic events occurring in the sun's atmosphere. There are also coronal mass ejections, or CMEs, which are equally impressive and potentially even more dangerous to our technological civilization. While a solar flare is primarily a burst of electromagnetic radiation, a CME is a massive ejection of actual matter, billions or even trillions of tons of plasma hurled into space at speeds that can exceed 1,000 kilometers per second. When you look at images of the sun taken in extreme ultraviolet light, you can often spot the dark regions that precede or accompany these eruptions. But there are other dark features on the sun as well. Features that might look ominous but actually reveal fascinating aspects of solar physics. These are called coronal holes, and they appear as darker regions because they're areas of cooler, less dense plasma compared to their surroundings. What makes coronal holes particularly interesting is their magnetic structure. Unlike other parts of the corona, where magnetic field lines form closed loops that arc back down to the sun's surface, the magnetic field lines in coronal holes are open. They stretch outward into space, creating pathways along which solar wind particles can escape more easily. It's like having express lanes on a highway. Particles following these open field lines can accelerate to much higher speeds than those trapped in closed magnetic structures. When these fast-moving streams of solar wind reach Earth and interact with our planet's magnetic field, the magnetosphere that shields us from harmful radiation, they can trigger one of nature's most beautiful displays, the aurora, also known as the northern and southern lights. These shimmering curtains of color dance across the sky in polar regions, painting the darkness with ethereal greens, reds, and purples. The aurora is essentially our atmosphere glowing as it's bombarded by energetic particles from the sun, a visible reminder of the invisible connection between our planet and our star. Using ultraviolet light gives scientists a much more detailed view of these fascinating solar features. The sun's outer layers are filled with structures that would be completely invisible if we only looked at visible light. There are solar filaments and prominences, enormous loops and arcs of plasma that rise from the photosphere and stretch hundreds of thousands of kilometers into the corona. These prominences are truly gargantuan structures. To appreciate their scale, imagine placing Earth next to one of these loops. Our entire planet would look like a tiny speck in comparison. Some prominences can be larger than the distance from Earth to the Moon, stretching more than 300,000 kilometers into space. They can form in as little as a single day, erupting from the sun's surface with surprising speed. Yet a stable prominence can persist in the corona for several months, slowly evolving and changing shape as magnetic forces play upon it. Watching a prominence form and evolve is like watching a cosmic ballet in slow motion. The plasma follows invisible magnetic field lines, tracing out elegant arcs and loops that would be impossible to predict without sophisticated computer models. Although the videos we see are sped up, dramatically compressing hours or days into mere minutes, when you consider the actual size and mass of material being moved, it becomes clear just how powerful the sun's magnetic fields truly are. We're talking about forces capable of lifting billions of tons of matter against the intense gravitational pull of a star. One of the most surprising discoveries about the sun's atmosphere is that it actually experiences something analogous to rain. Not the water rain we're familiar with on Earth, of course, but something equally fascinating: coronal rain. This phenomenon occurs when hot plasma ejected into the corona doesn't have enough energy to escape entirely into space. Instead, it becomes trapped by magnetic field lines, where it gradually cools over time. As it cools, it becomes denser and eventually falls back toward the sun's surface in glowing streams. Coronal rain is beautiful to observe, appearing as bright cascades that flow along magnetic field lines like water running down invisible channels in the sky. But don't let the familiar term fool you. This is still plasma with temperatures in the millions of degrees. It's rain that would instantly vaporize anything we could possibly imagine. The comparison to Earth's weather ends quickly when you consider the conditions involved. Of course, not all of the plasma in the corona falls gently back to the surface. Some of it remains suspended in magnetic structures until those structures become unstable. When that happens, the result can be explosive. The magnetic fields in the corona can become so twisted and stressed that they eventually snap, like an overstretched rubber band breaking. When this occurs, the result is a coronal mass ejection, a catastrophic release of magnetic energy that flings billions of tons of plasma into space at incredible velocities. Watching a CME develop and erupt is a breathtaking sight. In time-lapse observations, you can see magnetic structures gradually building up over hours or even days, slowly rising and expanding. There's often a period of relative calm where the structure seems stable, hovering above the sun's surface. Then, without warning, something changes. The structure destabilizes, the magnetic field lines reconnect in a new configuration, and suddenly an enormous mass of plasma is accelerating away from the sun at speeds that can reach several thousand kilometers per second. The power involved in these events is staggering. A large CME can eject more than 10 billion tons of matter that's roughly the mass of Mount Everest and accelerate it to a significant fraction of the speed of light. If you tried to calculate the kinetic energy involved, you'd need to write numbers with more than 25 zeros. It's the kind of energy that, if somehow captured and converted to electricity, could power human civilization for millions of years. When a CME is directed toward Earth, the consequences can be significant. Even though our planet has a powerful magnetic field that deflects most of the sun's radiation and particles, a direct hit from a major CME can overwhelm these defenses. The charged particles interact with Earth's magnetosphere, creating what's called a geomagnetic storm. During such storms, aurora can be seen at much lower latitudes than normal, sometimes as far south as the Caribbean or Mediterranean. But there's a darker side to these beautiful displays. The same charged particles that create aurora also induce electrical currents in power lines, pipelines, and other long-conducting structures. In extreme cases, these currents can be strong enough to damage transformers and cause widespread power outages. The largest geomagnetic storm in recorded history, the Carrington event of 1859, was powerful enough to set telegraph systems on fire and allow them to continue operating even after being disconnected from their batteries. If a storm of that magnitude struck today, it could cause trillions of dollars in damage and take years to fully repair. The relationship between the sun and Earth is far more intricate than simply providing warmth and light. Our star is the architect of an invisible environment that extends throughout the entire solar system, a domain shaped by magnetic fields, charged particles, and electromagnetic radiation. This realm, known as the heliosphere, is the sun's sphere of influence, and Earth exists deep within it, bathed in the continuous outflow of material and energy that streams away from the solar surface. At the heart of this relationship is the solar wind, a supersonic stream of charged particles, primarily electrons and protons, that flows outward from the sun in all directions. The solar wind originates in the sun's corona, where temperatures reach millions of degrees, and the particles have enough energy to escape the sun's gravitational pull. Near Earth, the solar wind typically travels at speeds between 300 and 800 kilometers per second, though during solar storms it can exceed 1,000 kilometers per second or more. The existence of the solar wind was not always obvious. For centuries, astronomers assumed that the space between the sun and planets was empty, a perfect vacuum devoid of matter. It was not until the middle of the 20th century that scientists began to realize this assumption was wrong. Observations of comet tails provided the first clues. Comets always develop tails that point away from the sun, regardless of the direction the comet is traveling. This suggested that some form of pressure or flow from the sun was pushing material away. In 1958, physicist Eugene Parker proposed a radical idea. The sun's corona was so hot that it must be continuously expanding outward, creating a steady wind of particles that filled the solar system. At the time, many scientists were skeptical. The concept of a stellar wind was new and untested, but Parker's theoretical work was vindicated just a few years later when spacecraft measurements confirmed the existence of the solar wind and measured its properties directly. The solar wind is not uniform. It varies in speed, density, and temperature depending on where in the corona it originates. The fastest streams come from coronal holes, those dark, magnetically open regions we discussed earlier where particles can escape more easily along open magnetic field lines. Slower, denser streams emerge from the streamer belt near the sun's equator, where magnetic field lines are more tangled and closed. As the sun rotates, these fast and slow streams sweep past Earth like the rotating beam of a lighthouse, creating variations in the space environment around our planet. When the solar wind reaches Earth, it does not simply pass by unnoticed. Our planet is protected by its own magnetic field, the magnetosphere, which extends tens of thousands of kilometers into space. The magnetosphere acts as a shield, deflecting most of the solar wind around the planet. But it is not a perfect barrier. The interaction between the solar wind and the magnetosphere is complex and dynamic, creating a bow shock on the sun-facing side where the wind slows and heats as it encounters Earth's magnetic field. On the night side of Earth, the magnetosphere is stretched out into a long tail that extends far beyond the moon's orbit. Within this magnetotail, magnetic field lines from opposite sides of the tail can reconnect, releasing energy and accelerating particles back toward Earth. When these energized particles collide with the upper atmosphere near the poles, they excite atoms of oxygen and nitrogen, causing them to emit light in the form of the aurora borealis and aurora australis, the northern and southern lights. Aurora are among nature's most spectacular displays, shimmering curtains and arcs of green, red, purple, and blue that dance across the polar skies. Indigenous cultures around the world have long been fascinated by these lights, weaving them into myths and legends. In Norse mythology, the aurora were believed to be reflections from the shields of the Valkyries, warrior maidens who chose which soldiers would die in battle. In Inuit tradition, the lights were spirits of the dead playing games in the sky. Today, we understand the aurora as a direct manifestation of the connection between Earth and the sun, a visible reminder that our planet does not exist in isolation but is part of a vast, interconnected system. Yet the aurora are just one of many ways in which the sun's activity affects our world. More subtle and potentially more dangerous are the effects of space weather, the term scientists use to describe the changing conditions in the space environment driven by solar activity. Space weather can have profound impacts on modern technology. When a powerful solar flare erupts, it releases a burst of X-rays and ultraviolet radiation that reaches Earth in just 8 minutes. This radiation can ionize the upper layers of Earth's atmosphere, disrupting radio communications. especially high-frequency signals used by aircraft and ships for long-distance communication. GPS signals, which rely on precise timing and travel through the ionosphere, can also be degraded, leading to navigation errors. Even more concerning are the effects of coronal mass ejections. When a large CME strikes Earth's magnetosphere, it can trigger a geomagnetic storm, a major disturbance in Earth's magnetic field that lasts for hours or days. During such storms, the magnetosphere is compressed and energy is injected into the system, causing electric currents to flow in the ionosphere and even in the ground. These currents can induce voltages in long conductors such as power lines, pipelines, and undersea cables. In extreme cases, these induced currents can damage transformers and electrical grids, leading to widespread blackouts. The most famous example occurred in March of 1989, when a geomagnetic storm caused by a solar eruption knocked out power across the entire province of Quebec, Canada, leaving 6 million people without electricity for up to 9 hours. Transformers were damaged, and repairs took months. Had the storm been even more powerful, or had it struck a more densely populated and technologically dependent region, the consequences could have been far worse. The largest geomagnetic storm in recorded history is known as the Carrington event, named after British astronomer Richard Carrington, who observed the solar flare that triggered it in September of 1859. At that time, the most advanced technology was the telegraph system, which connected cities across continents with networks of wires. When the geomagnetic storm struck, telegraph operators reported sparks flying from their equipment, paper catching fire, and some systems continuing to send messages even after being disconnected from their batteries, powered solely by the currents induced by the storm. If a storm of similar magnitude were to strike today, the consequences would be catastrophic. Modern civilization depends on electrical power, telecommunications, satellite navigation, and the internet, all of which are vulnerable to space weather. Estimates suggest that a Carrington-scale event could cause trillions of dollars in damage and take years to fully recover from, as critical infrastructure would need to be rebuilt and replaced. Recognizing these risks, space agencies and governments around the world have invested in monitoring the sun and providing early warnings of potentially dangerous solar activity. Satellites such as the Solar Dynamics Observatory, the Solar and Heliospheric Observatory, and the recently launched Parker Solar Probe observe the sun continuously, watching for flares and CMEs. When a major eruption is detected, warnings are issued to power companies, airlines, satellite operators, and other stakeholders, giving them time to take protective measures. The Parker Solar Probe, launched in 2018, is one of the most ambitious solar missions ever attempted. Unlike previous spacecraft that observed the sun from a distance, Parker is designed to fly directly through the sun's corona, approaching to within 6 million kilometers of the solar surface, closer than any spacecraft has ever ventured. At this distance, temperatures in the corona can exceed 1,000,000 degrees. Yet the probe is protected by a cutting-edge heat shield that can withstand temperatures up to 1,400 degrees Celsius while keeping its instruments at a comfortable room temperature. By flying through the corona, Parker is gathering data on the solar wind's origin, the processes that heat the corona to such extreme temperatures, and the mechanisms that accelerate particles to nearly the speed of light. These measurements are helping scientists build more accurate models of the sun's behavior and improve predictions of space weather, ultimately making our technological infrastructure more resilient. But the sun's influence extends beyond space weather and geomagnetic storms. There is growing evidence that solar activity also affects Earth's climate. Though the connections are complex and often subtle, the most obvious link is the sun's total energy output, which varies slightly over the 11-year solar cycle. During solar maximum, the sun is about 0.1% brighter than during solar minimum, a small change, but one that can have measurable effects on Earth's climate system. More significant are the variations in ultraviolet radiation, which can change by several percent or more over the solar cycle. Ultraviolet light is absorbed in the stratosphere, the layer of Earth's atmosphere that lies above the weather-producing troposphere. Changes in ultraviolet input can alter temperatures and circulation patterns in the stratosphere, which in turn can influence weather patterns at the surface. Some studies have found correlations between solar activity and regional climate phenomena such as monsoon intensity, storm tracks, and even hurricane frequency, though these relationships are still being investigated and debated. Another intriguing connection involves cosmic rays, high-energy particles from outside the solar system that constantly bombard Earth. The solar wind and the sun's magnetic field act as a shield against cosmic rays, deflecting many of them before they can reach the inner solar system. During solar maximum, when the solar wind is stronger and the magnetic field more extended, fewer cosmic rays reach Earth. During solar minimum, the shield weakens and cosmic ray intensity increases. Cosmic rays can ionize molecules in Earth's atmosphere, and some researchers have proposed that this ionization might influence cloud formation. The idea, still controversial, is that cosmic rays could seed the formation of tiny aerosol particles that serve as nuclei for cloud droplets. If true, this would create a link between solar activity and cloudiness, which in turn affects how much sunlight reaches Earth's surface and how much heat is trapped by the atmosphere. The hypothesis remains unproven and contentious, with many scientists skeptical that the effect is strong enough to significantly influence global climate. Nevertheless, it illustrates how interconnected the Sun and Earth truly are, and how much remains to be learned about the subtle ways in which our star shapes the environment we live in. Beyond these physical connections, there is even evidence that solar activity influences biological and social systems on Earth, though these effects are less well understood and often controversial. Some studies have found correlations between solar cycles and patterns of disease outbreaks, agricultural yields, and even stock market fluctuations. The mechanisms behind such correlations, if they are real, are unclear. It may be that solar-induced changes in climate and weather create conditions that favor or disfavor certain crops, pests, or pathogens. Or it could be that the correlations are coincidental, artifacts of the limited data available. One particularly fascinating area of research involves the potential effects of space weather on human health. During solar storms, radiation levels increase at high altitudes and high latitudes, posing risks to astronauts and airline passengers. There is also some evidence that geomagnetic disturbances might affect biological rhythms and cardiovascular health, though the data is sparse and more research is needed to draw firm conclusions. What is clear is that the Sun is not a static, unchanging backdrop to life on Earth. It is a dynamic, variable star whose activity follows predictable cycles, but also exhibits unpredictable outbursts. Understanding these cycles and their effects is not just an academic exercise. It is a practical necessity for a civilization that depends increasingly on technology vulnerable to solar storms. The 11-year solar cycle is the most prominent pattern in the Sun's activity, but it is not the only one. Sunspot records dating back to the early 17th century reveal longer-term variations as well. For instance, between 1645 and 1715, a period known as the Maunder Minimum, sunspots almost completely disappeared for several decades. This extended quiet period coincided with the coldest phase of the Little Ice Age, a time of unusually cold winters and poor harvests in Europe. Whether the Maunder Minimum caused the cooling or merely coincided with it is still debated. The total change in solar output during such grand minima is small, on the order of 0.2 to 0.3%, which seems insufficient to explain the observed climate changes. However, when combined with other factors such as volcanic eruptions and changes in ocean circulation, even small solar variations might have tipped the balance. Conversely, there have been periods of unusually high solar activity, such as the modern maximum that lasted from the mid-20th century until the early 2000s. During this time, the Sun was more active than it had been in centuries, with frequent and powerful solar storms. Some researchers have suggested that this period of high activity contributed to the warming observed in the 20th century, though the consensus among climate scientists is that the dominant driver of recent warming is the increase in greenhouse gases from human activities, not changes in solar output. Looking forward, predicting the Sun's future activity is a major challenge. While the 11-year cycle is fairly regular, the amplitude of each cycle, how many sunspots appear, and how strong solar storms become varies unpredictably. Solar cycle 24, which peaked around 2014, was the weakest in a century, leading some scientists to speculate that the Sun might be entering another grand minimum. However, the current cycle, solar cycle 25, appears to be more active than initially predicted, suggesting that any trend toward lower activity may be paused or reversed. Improving our ability to forecast solar activity, both in the short-term hours to days ahead of a specific storm, and in the long term predicting the strength of future solar cycles, is a major goal of solar physics. Better forecasts would allow power companies, satellite operators, and other vulnerable industries to prepare for storms, reducing the risk of damage and disruption. Achieving this goal requires not just better observations, but also better theoretical understanding of the solar dynamo, the process deep within the sun that generates and amplifies its magnetic field. The dynamo is driven by the interplay of rotation, convection, and magnetic fields, but the details are fiendishly complex and not yet fully understood. Supercomputer simulations are beginning to reproduce some of the sun's observed behavior, but there is still much work to be done. As we delve deeper into the sun's mysteries, we realize that this seemingly simple ball of glowing gas is anything but simple. It is a dynamic, evolving system governed by the laws of physics, but exhibiting behaviors that are chaotic and difficult to predict. It is a laboratory for studying plasma physics, magnetohydrodynamics, and nuclear reactions under conditions that cannot be replicated on Earth. And it is a constant reminder that our planet exists not in isolation, but as part of a vast and interconnected cosmos. The sun has been humanity's constant companion throughout history, shaping cultures, driving exploration, and inspiring countless works of art, literature, and science. Ancient civilizations worshipped the sun as a god, recognizing its central role in sustaining life. The Egyptians revered Ra, the sun god who traveled across the sky each day in a golden boat. The Aztecs built great pyramids aligned with the solstices and equinoxes, marking the sun's passage through the seasons. In Greece, Helios drove his chariot across the heavens, bringing light to the world. Even as science replaced mythology with understanding, the sun retained its central place in human thought. The realization that Earth orbits the sun, rather than the other way around, was one of the most profound intellectual revolutions in history, overturning centuries of geocentric dogma and opening the door to modern astronomy. Galileo's observations of sunspots challenged the Aristotelian belief that the heavens were perfect and unchanging. Newton's laws of motion and gravity explained the mechanics of planetary orbits, unifying the heavens and the Earth under a single set of physical principles. In the 20th century, the development of nuclear physics revealed the source of the sun's energy, solving a mystery that had puzzled scientists for generations. How could the sun shine so brightly for billions of years without running out of fuel? The answer: nuclear fusion not only explained the sun, but also illuminated the life cycles of all stars, showing that the elements that make up planets and living beings were forged in stellar cores and scattered across the galaxy by supernova explosions. Today, as we stand on the threshold of becoming a spacefaring civilization, our relationship with the sun is evolving once again. We are learning to harness solar energy, capturing a tiny fraction of the sun's output and converting it into electricity to power our cities and industries. We are sending probes to touch the sun's corona, gathering data that will help protect our technology and infrastructure from solar storms. And we are beginning to look beyond our own solar system, searching for planets around other stars and wondering if they, too, might harbor life warmed by the light of distant suns. The story of the sun is far from over. Every new observation, every new mission, every new theoretical breakthrough adds another chapter to our understanding. And as we continue to explore this nearest star, we are reminded that the universe is vast, complex, and full of wonders waiting to be discovered. Yet amid all this scientific progress, there remains something deeply humbling about the Sunday. For all our knowledge, for all our technology, we are still utterly dependent on this single star. If the sun were to suddenly vanish, life on Earth would end within days. The temperature would plummet, the oceans would freeze, and photosynthesis, the foundation of the food chain, would cease. We are creatures of the sun, shaped by its light and warmth, bound to its rhythms and cycles. This dependence is not a weakness, but a connection, a reminder that we are part of something larger than ourselves, part of a cosmic dance that has been unfolding for billions of years and will continue long after we are gone. The sun is not just a star in the sky, it is our star, the source of everything we know and everything we are. As we look toward the future, the sun will continue to guide us. It will illuminate new discoveries, power new technologies, and inspire new generations to look up at the sky and wonder. And perhaps, one day, when humanity has spread beyond Earth to explore the solar system and beyond, we will look back at the sun from distant worlds and appreciate it in a new way, not just as the star that gave us life, but as the star that gave us the courage to reach for the stars. For now, though, let us return to the present, to the detailed mechanisms and cycles that govern the sun's behavior. We have explored its structure from the photosphere down to the core, and we have seen how its energy travels outward through the layers. We have witnessed its violent eruptions and felt the reach of its influence across the solar system. But there is still more to understand, particularly about the cycles that modulate all this activity. The solar cycle, that 11-year rhythm that governs the rise and fall of sunspots and solar storms, is one of the most fundamental patterns in our solar system. Yet despite centuries of observation, the mechanisms that drive this cycle are still not fully understood. What we do know is that the cycle is intimately connected to the sun's magnetic field, which is constantly being generated, twisted, and reorganized by the complex motions of plasma deep within the solar interior. The generation of the sun's magnetic field begins in the convective zone and the tachocline beneath it. Here, electrically conducting plasma moves in complex patterns, driven by convection currents and differential rotation. The sun does not rotate as a solid body. Instead, its equatorial regions complete a rotation in about 25 days, while regions near the poles take more than 30 days. This differential rotation stretches and winds up magnetic field lines like twisting a rubber band. As these field lines become increasingly tangled and amplified, they eventually rise through the convective zone and break through the photosphere, forming the loops and arches we see as active regions, prominences, and sunspots. The strongest concentrations of magnetic field appear as sunspot pairs, with one spot marking where field lines emerge from below the surface and the other marking where they plunge back down. Between these spots, the field lines arch high into the corona, creating the glowing loops visible in ultraviolet and X-ray images. Over the course of a solar cycle, the number and location of sunspots change in a predictable pattern. At the beginning of a new cycle, shortly after solar minimum, the first sunspots appear at relatively high latitudes, around 30 to 40 degrees north and south of the equator. As the cycle progresses toward solar maximum, more sunspots appear, and they form at progressively lower latitudes. By the time the cycle reaches its peak, sunspots are appearing close to the equator, and their numbers have increased dramatically. After solar maximum, the number of sunspots begins to decline, and the active regions continue to migrate toward the equator until the cycle ends and a new one begins. If you plot the latitude of sunspots over time, the result is a distinctive pattern known as the butterfly diagram, named for its resemblance to the wings of a butterfly spreading outward and then closing as each cycle progresses. But the solar cycle is more than just a count of sunspots. It represents a complete reversal of the sun's global magnetic field. At the beginning of a cycle, the sun's magnetic field has a certain polarity. Let's say the north magnetic pole is at the top and the south at the bottom. Over the course of the 11-year cycle, this field gradually weakens, disappears, and then reemerges with the opposite polarity. The north and south magnetic poles have switched places. After another 11 years, they switch back. Thus, the full magnetic cycle of the sun actually takes about 22 years, though the sunspot cycle is only 11. This reversal is not instantaneous or uniform. Different parts of the sun's magnetic field reverse at different times, creating complex and often chaotic patterns during the transition. Solar maximum, when sunspot numbers peak, is typically the time when the magnetic field is most disordered and the sun's activity is most intense. This is when solar flares and coronal mass ejections are most frequent and most powerful. The exact timing and strength of each solar cycle varies. Some cycles are strong, with many sunspots and frequent storms. Others are weak, with few sunspots and relatively quiet conditions. Scientists use the smooth sunspot number, a monthly average that filters out short-term fluctuations, to track and compare cycles. The strongest cycle on record was solar cycle 19, which peaked in 1958 with a smooth sunspot number exceeding 200. In contrast, solar cycle 24, which peaked around 2014, had a maximum sunspot number of only about 80, making it the weakest cycle in more than a century. Predicting the strength and timing of future solar cycles is a major challenge. Many methods have been tried, ranging from statistical extrapolations of past cycles to complex computer models of the solar dynamo. Some predictions are based on observations of the sun's polar magnetic field during solar minimum, which appears to be correlated with the strength of the next cycle. Others use measurements of the speed of plasma flows beneath the photosphere, detected through helioseismology, to forecast when and where the next active regions will emerge. Despite these efforts, solar cycle predictions remain uncertain. The sun is a chaotic system, and small changes in initial conditions can lead to large differences in outcomes. This unpredictability is frustrating for scientists and space weather forecasters. But it also makes the sun an endlessly fascinating subject of study. Beyond the 11-year cycle, there are hints of longer-term variations in solar activity. Historical records of sunspot observations, some dating back more than 4 centuries, reveal periods when the sun was unusually quiet or unusually active for extended periods. The Maunder minimum from 1645 to 1715 was one such period. During these 70 years, sunspots were extremely rare, and the solar cycle seemed to be suppressed or even absent. Other grand minima have been identified in the historical record, including the Spur minimum in the 15th century and the Dalton minimum in the early 19th century. There is also evidence from isotopes in tree rings and ice cores of similar grand minima occurring over the past 10,000 years. These isotopes, such as carbon-14 and beryllium-10, are produced when cosmic rays interact with Earth's atmosphere. Because the solar wind modulates the flux of cosmic rays reaching Earth, changes in solar activity leave a fingerprint in these isotopes. By analyzing these records, scientists have found that grand minima occur roughly once or twice per century on average, though the timing is irregular. Conversely, there are periods of elevated activity, such as the modern maximum of the 20th century, when the sun was more active than it had been in many centuries. The causes of these long-term variations are still debated. They may be related to fluctuations in the solar dynamo, perhaps triggered by changes in the flow patterns deep within the convective zone, or by interactions between different layers of the sun's interior. Some researchers have suggested that the solar cycle is influenced by the gravitational pull of the planets, particularly Jupiter and Saturn, though this idea remains controversial and lacks strong supporting evidence. Understanding these long-term variations is important not just for predicting future solar activity, but also for understanding the sun's influence on Earth's climate over centuries and millennia. While solar variability is not the primary driver of recent climate change, that distinction belongs to human-caused greenhouse gas emissions. It has played a role in past climate variations, and it will continue to be a factor in the future. One of the most intriguing aspects of the solar cycle is its effect on the sun's internal structure. As the magnetic field waxes and wanes, it exerts forces on the plasma within the sun, slightly altering the flow patterns and even changing the shape of the sun itself. During solar maximum, the sun is very slightly more oblate, flattened at the poles, and bulging at the equator compared to solar minimum. The difference is tiny, only a few parts per million, but it can be measured using precise observations of the sun's shape and oscillations. These subtle changes have implications for the solar dynamo and for our understanding of how magnetic fields are generated and maintained in stars. They also provide a window into processes occurring deep within the sun that cannot be observed directly. By combining observations of the sun's surface and atmosphere with helioseismology and computer models, scientists are gradually piecing together a comprehensive picture of the solar interior and the dynamo that powers the solar cycle. The solar cycle also affects the heliosphere, the vast bubble of space dominated by the solar wind and the sun's magnetic field. The heliosphere extends far beyond the orbits of the planets, reaching more than 100 times the distance from the sun to Earth. At its outer edge, the solar wind slows and merges with the interstellar medium, the gas and dust between the stars, creating a boundary known as the heliopause. The Voyager 1 and Voyager 2 spacecraft, launched in 1977, have both crossed the heliopause and entered interstellar space, making them the first human-made objects to leave the sun's domain. Their measurements revealed that the heliopause is not a smooth spherical boundary, but a dynamic, rippled interface shaped by the pressure of the solar wind pushing outward and the interstellar medium pushing inward. The shape and size of the heliosphere change over the solar cycle. During solar maximum, when the solar wind is stronger and more variable, the heliosphere expands slightly. During solar minimum, it contracts. These changes affect the cosmic ray environment throughout the solar system, with implications for space exploration and even for the evolution of planetary atmospheres over geological timescales. For astronauts and spacecraft venturing beyond Earth's protective magnetosphere, understanding the solar cycle is critical. During solar maximum, the risk of exposure to harmful radiation from solar flares and CMEs is higher. Mission planners must take this into account when scheduling spacewalks, planning lunar or Martian missions and designing shielding for spacecraft and habitats. Conversely, during solar minimum, the increased flux of galactic cosmic rays poses its own set of challenges, as these particles can penetrate deeper into spacecraft and pose long-term health risks. The sun's influence extends even to the climates of other planets in the solar system. Mars, with its thin atmosphere and lack of a global magnetic field, is particularly vulnerable to the solar wind, which gradually strips away atmospheric gases over time. This process, occurring over billions of years, has transformed Mars from a world that may once have had liquid water on its surface into the cold, dry desert we see today. Jupiter and Saturn, with their powerful magnetic fields and thick atmospheres, are less affected by the solar wind, but they still experience their own versions of space weather. Aurora on these giant planets can be even more spectacular than those on Earth, driven not just by the solar wind, but also by volcanic activity on Jupiter's moon Io, which injects charged particles into Jupiter's magnetosphere. Even distant Pluto, at the edge of the solar system, is not beyond the sun's reach. The New Horizons spacecraft, which flew past Pluto in 2015, detected interactions between the solar wind and Pluto's thin atmosphere, showing that even at distances of more than 5 billion kilometers from the sun, the solar wind remains a significant force. As we continue to explore the solar system, our understanding of the sun's influence grows. Every mission, every new set of data adds to the picture. The sun is not just the center of the solar system in a gravitational sense. It is the central actor in a vast, interconnected system of planets, moons, asteroids, comets, and dust, all bound together by gravity and bathed in the light and particles streaming outward from our star. Yet for all the progress that has been made, fundamental questions remain. Why does the solar cycle have a period of roughly 11 years? Why do some cycles peak strongly while others remain weak? What triggers grand minima and grand maxima? How exactly does the solar dynamo work, and how do the different layers of the sun's interior communicate and influence each other? Answering these questions will require continued observations, more sophisticated computer models, and perhaps new theoretical insights that have not yet been imagined. The sun, despite being the closest star and the most intensely studied object in astronomy, still holds many secrets. One area of active research is the long-standing mystery of why the sun's corona is so much hotter than the photosphere below it. The photosphere has a temperature of about 5,500 degrees Celsius, while the corona reaches temperatures of 1 to 2 million degrees or more. This seems to violate the intuitive expectation that temperature should decrease as you move away from a heat source, much like the air gets colder as you climb a mountain away from the warm surface. For decades, scientists have proposed various mechanisms to explain coronal heating. One idea is that magnetic waves, generated by the churning motions of the convective zone, propagate upward into the corona and deposit their energy as heat. These waves, known as Alfvén waves, travel along magnetic field lines and can carry energy efficiently through the solar atmosphere. When the waves dissipate or interact with each other, they release their energy, heating the surrounding plasma. Another possibility is that the heating comes from countless small-scale magnetic reconnection events, sometimes called nanoflares. According to this theory, the corona is filled with myriads of tiny loops and strands of magnetic field that are constantly shifting and reconnecting. Each reconnection event releases a small burst of energy, and the cumulative effect of billions of these events heats the corona to its observed temperature. Recent observations from spacecraft like the Parker Solar Probe are providing new clues to this mystery. By flying through the corona itself, Parker is measuring the properties of the plasma and magnetic field at close range, allowing scientists to test and refine their theories. Early results suggest that both waves and reconnection may play important roles, and that the heating process varies depending on location and the structure of the magnetic field. Understanding coronal heating is not just an academic puzzle. The corona is the source of the solar wind, and the temperature and density of the corona determine the properties of the wind that fills the solar system. By understanding how the corona is heated, scientists can better predict the solar wind's behavior and its effects on Earth and other planets. Another frontier in solar physics is the study of solar energetic particles, or SEPs. These are charged particles, mostly protons, but also heavier ions that are accelerated to extremely high energies during solar flares and CMEs. SEPs can reach nearly the speed of light, carrying enormous amounts of kinetic energy. When they strike spacecraft, astronauts, or planetary atmospheres, they can cause significant damage. SEPs are a major concern for human space exploration. During a large solar event, the flux of energetic particles can increase by orders of magnitude within minutes, creating a radiation environment that would be lethal to unprotected astronauts. Even inside a spacecraft or habitat, the dose of radiation can be dangerously high if the shielding is insufficient. For missions to the Moon or Mars, where astronauts would be exposed for months or years, understanding and predicting SEP events is a top priority. Scientists are working to understand how and where particles are accelerated during solar eruptions. It appears that both the magnetic reconnection in flares and the shock waves driven by CMEs can accelerate particles, but the details are complex and depend on the specific structure and evolution of each event. Observations from multiple spacecraft, combined with advanced computer simulations, are gradually revealing the physical processes at work. Looking even further ahead, researchers are beginning to think about how to forecast space weather in the same way that meteorologists forecast terrestrial weather. Just as weather forecasts rely on a combination of observations, physical understanding, and computer models, space weather forecasting will require continuous monitoring of the sun, real-time data transmission, and sophisticated models that can predict the propagation of solar wind, CMEs, and energetic particles through the heliosphere. Such forecasting is already underway, but it is still in its early stages. Current models can predict the arrival of a CME at Earth with an accuracy of several hours, which is useful, but not ideal. Improving the accuracy and lead time of these forecasts is a major goal, one that will require better observations of the sun's far side, more powerful computers, and deeper understanding of the underlying physics. In addition to protecting technology and astronauts, space weather forecasting has potential applications in other areas as well. For example, airlines could use forecasts to reroute flights away from polar regions during radiation storms, reducing the exposure of passengers and crew. Satellite operators could adjust the orbits or operations of their spacecraft to minimize damage during geomagnetic storms. Power companies could prepare for potential disruptions to the electrical grid, reducing the risk of large-scale blackouts. As our society becomes more dependent on technology, the importance of space weather forecasting will only grow. Just as we take for granted the availability of weather forecasts for planning our daily activities, we may soon come to rely on space weather forecasts to ensure the reliable operation of the infrastructure we depend on. But beyond the practical applications, there is a deeper reason to study the sun. Curiosity. The sun is a natural laboratory for physics, a place where matter and energy behave in ways that cannot be replicated on Earth. By studying the sun, we learn about nuclear fusion, plasma physics, magnetic fields, and the fundamental processes that govern the universe. The knowledge gained from solar research has applications far beyond the sun itself. Understanding how stars generate energy through fusion is key to developing fusion power on Earth, a potential source of clean, abundant energy for the future. Understanding how magnetic fields behave in plasmas is important for designing fusion reactors and for interpreting observations of other astrophysical objects, from distant stars to supermassive black holes. The sun also serves as a benchmark for understanding other stars. Almost everything we know about stellar structure, evolution, and behavior comes from studying the sun and then extrapolating to stars of different masses, temperatures, and ages. Observations of the sun provide the detailed, close-up view that is impossible to obtain for other stars, no matter how powerful our telescopes. In recent years, astronomers have discovered thousands of planets orbiting other stars, and many of these planets lie within their star's habitable zone, the region where temperatures might allow liquid water to exist on the surface. Understanding the sun's variability and its effects on Earth's climate and habitability helps us predict the conditions on these distant worlds and assess their potential to support life. If we are to find life elsewhere in the universe, we must first understand how life arose and persisted on Earth. And that understanding is intimately tied to the sunday, the energy that drives photosynthesis, the cycles that govern climate, the magnetic shield that protects Earth from harmful radiation. All of these are gifts from the sunday. By studying our own star, we learn what to look for around other stars. As we draw this exploration toward its conclusion, it is worth reflecting on the journey we have taken. We began at the outermost layers of the sun's atmosphere, the corona, where temperatures soar to millions of degrees and where violent eruptions send plasma and radiation streaming across the solar system. We descended through the transition region and the chromosphere, witnessing the delicate spicules and the turbulent convection that drives energy upward from below. We explored the photosphere, the visible surface of the sun, with its sunspots and granules. And we learned how these features are connected to the magnetic fields generated deep within the solar interior. We journeyed backward in time to the birth of the sun, tracing its origins to a giant molecular cloud enriched by the remnants of ancient stars. And we followed the process of collapse, fragmentation, and ignition that led to the formation of our star and the solar system around it. We delved into the core, where nuclear fusion converts hydrogen into helium and releases the energy that powers the sunday. We traced the tortuous path of photons as they random walk through the radiative zone, crossing the tachocline and convecting through the outer layers until they finally escape into space. And we explored the solar cycle, the 11-year rhythm that governs the sun's activity and influences everything from space weather to Earth's climate. Throughout this journey, one theme has emerged again and again. The sun is dynamic, complex, and interconnected. Every layer influences the others, and changes in one part of the sun ripple outward to affect the entire solar system. The sun is not a static object, but a living, evolving entity, constantly in motion, constantly changing, and yet remarkably stable over the timescales that matter to life on Earth. And through it all, humanity has been watching, learning, and adapting. From ancient sun worshippers to modern astrophysicists, from Galileo's first observations of sunspots to the Parker Solar Probe's daring flights through the corona, our relationship with the sun has evolved, but our fascination has never waned. As we look to the future, new missions and new technologies will continue to push the boundaries of our understanding. The Daniel K. Inouye Solar Telescope, the largest solar telescope in the world, is already producing the highest resolution images of the sun's surface ever captured, revealing details as small as 30 kilometers across. Future space missions may place observatories at vantage points around the solar system, providing a three-dimensional view of the sun and its eruptions. There is even talk of sending probes even closer to the sun than Parker, perhaps using advanced heat shields and propulsion systems to skim just above the photosphere. Such missions would be incredibly challenging, but they would provide unprecedented insights into the sun's behavior and the processes that drive its activity. And perhaps, in the more distant future, human beings will stand on the surface of the moon or Mars and watch the sun rise over alien horizons, seeing our star from perspectives that no human has ever experienced. These future explorers will need to understand the sun's behavior intimately, not just for scientific curiosity, but for their very survival. They will rely on accurate space weather forecasts, robust radiation shielding, and a deep understanding of how the sun influences the environments of other worlds. The sun will also play a central role in humanity's energy future. As the world transitions away from fossil fuels to combat climate change, solar energy is becoming increasingly important. Photovoltaic panels that convert sunlight directly into electricity are now among the cheapest sources of power in many parts of the world. Solar farms covering vast areas of desert or floating on reservoirs are generating gigawatts of clean, renewable energy. But even more ambitious concepts are on the horizon. Some visionaries have proposed building massive solar power stations in space, where sunlight is available 24 hours a day without being filtered by the atmosphere or blocked by clouds. These stations would collect solar energy and beam it back to Earth using microwaves or lasers, providing a constant supply of clean power. While such projects face enormous technical and economic challenges, they represent one possible path toward a sustainable energy future. Beyond practical applications, the sun continues to inspire wonder and awe. Every sunrise and sunset, every solar eclipse, every display of the aurora reminds us of the beauty and power of our nearest star. Artists, poets, and musicians have drawn inspiration from the sun for millennia, and that creative wellspring shows no signs of running dry. The sun has also played a central role in some of humanity's greatest scientific achievements. The discovery that the sun is powered by nuclear fusion led directly to our understanding of how all stars work and how the elements were created. The realization that the sun formed from the remnants of earlier stars revealed the cosmic cycle of birth, death, and rebirth that has been unfolding for billions of years. And the recognition that the sun's activity affects Earth in profound ways has opened up an entirely new field of research connecting astronomy, geophysics, climatology, and even biology. Yet as much as we have learned, there is still so much we do not know. The precise mechanisms of the solar dynamo remain elusive. The causes of long-term variations in solar activity are still debated. The details of how energy is transported through the sun's interior, how the corona is heated, and how particles are accelerated to relativistic speeds are all areas of active research where major questions remain unanswered. One of the most profound mysteries concerns the sun's ultimate fate. We know from theory and from observations of other stars that the sun will eventually exhaust the hydrogen in its core and begin to evolve off the main sequence. In about 5 billion years, the core will contract and heat up, igniting a shell of hydrogen surrounding the inert helium core. This will cause the sun's outer layers to expand dramatically, transforming it into a red giant. During this phase, the sun will swell to hundreds of times its current size, engulfing the orbits of Mercury and Venus. Whether Earth will be swallowed as well is uncertain. Some calculations suggest that as the sun loses mass through its expanding outer layers, Earth's orbit will migrate outward just enough to avoid being consumed. Other models predict that tidal forces and drag from the sun's extended atmosphere will cause Earth to spiral inward to its doom. Even if Earth survives the red giant phase, it will be rendered uninhabitable. The intense heat will boil away the oceans, strip away the atmosphere, and turn the surface into a hellish, molten wasteland. Any life that still exists on Earth by that time will need to have found a way to leave the planet, perhaps migrating to the outer solar system, where the moons of Jupiter and Saturn might become temperate havens in the warmth of the swollen sunday. Eventually, the sun's core will become hot enough to ignite helium fusion, converting helium into carbon and oxygen. This process, known as the helium flash, will occur suddenly and release an enormous amount of energy, though it will be largely absorbed by the surrounding layers and not be visible from outside. For a time, the sun will stabilize as a helium-burning star, shining with a luminosity far greater than it does today. But helium, like hydrogen, is a finite fuel. After a few 100 million years, the helium in the core will be exhausted, and the sun will once again face a crisis. It will attempt to fuse heavier elements, but it lacks the mass necessary to ignite carbon fusion. Instead, the core will contract into a hot, dense ember, composed mostly of carbon and oxygen, supported not by fusion or gas pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. At the same time, the outer layers of the sun will be blown away in a series of gentle pulsations, forming a glowing shell of gas known as a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. They were named by early astronomers who thought their round, disc-like appearance resembled planets seen through a telescope. These nebulae are among the most beautiful objects in the night sky, glowing in vibrant colors as the intense ultraviolet light from the exposed core ionizes the surrounding gas. The core itself, now stripped of its outer layers, will shine as a white dwarf, a stellar remnant roughly the size of Earth, but with a mass comparable to the sun's current mass. A teaspoon of white dwarf material would weigh several tons on Earth. The white dwarf will radiate away its residual heat over billions of years, gradually cooling and fading until it becomes a cold, dark cinder known as a black dwarf. However, the universe is not yet old enough for any white dwarfs to have cooled to this final state. This is the sun's destiny, and it is the fate of all stars similar in mass to our own. More massive stars will end their lives more dramatically, as supernovae or even as black holes. But the sun's ending will be relatively peaceful. It will fade quietly into the night, leaving behind a faint remnant and a nebula that will enrich the interstellar medium with the heavy elements forged in its core. Those elements, carbon, oxygen, nitrogen, and others, will become part of future generations of stars and planets. In this way, the cycle continues. The sun was born from the ashes of earlier stars, and its own ashes will, in turn, give rise to new stars, new planets, and perhaps new forms of life. It is a humbling thought. The atoms in our bodies, the oxygen we breathe, the calcium in our bones, were all created in stars that lived and died long before the sun was born. This cosmic perspective reminds us of our place in the universe. We are not separate from the cosmos, but part of it, products of billions of years of stellar evolution. We are, in a very real sense, made of stardust, and the sun is the latest chapter in a story that stretches back to the Big Bang and will continue far into the future. But we need not wait billions of years to appreciate the sun's significance. Every day, it provides the energy that sustains life on Earth. Plants capture sunlight through photosynthesis, converting it into chemical energy that flows through the food chain, feeding animals, fungi, and countless microorganisms. The sun drives the water cycle, evaporating water from the oceans and lifting it into the atmosphere, where it forms clouds, falls as rain, and fills rivers and lakes. It powers the winds and ocean currents, distributing heat around the planet and shaping the climate. Even fossil fuels, coal, oil, and natural gas are ancient sunlight, captured by plants and plankton hundreds of millions of years ago and stored underground in concentrated form. When we burn these fuels, we are releasing energy that the sun delivered to Earth in the distant past. In a sense, almost all of the energy we use, with the exception of nuclear and geothermal power, ultimately comes from the sun. This dependence makes the sun not just an astronomical object, but a partner in Earth's story. The evolution of life on our planet has been shaped by the sun's light and warmth. Changes in Earth's orbit and axial tilt, which alter the distribution of sunlight across the planet's surface, have driven ice ages and warm periods over geological time. Variations in the sun's output, though small, have influenced climate and may have played a role in historical events such as the Little Ice Age. Looking forward, the relationship between the sun and Earth will continue to evolve. As the sun gradually brightens over the next billion years, even while it remains on the main sequence, Earth's climate will warm. Eventually, the increased solar luminosity will trigger a runaway greenhouse effect, boiling away the oceans and rendering the planet uninhabitable long before the sun enters its red giant phase. Life on Earth, at least in the forms we know today, has a finite lifespan measured in hundreds of millions of years, not billions. This sobering realization underscores the preciousness of our current moment in cosmic history. We live on a planet in the habitable zone of a stable, middle-aged star, a configuration that has allowed complex life to evolve and thrive for billions of years, and will continue to do so for hundreds of millions more. It is a rare and fortunate circumstance, one that we should not take for granted. At the same time, this awareness can inspire us to think beyond our own planet and our own time. If life on Earth is ultimately finite, then perhaps our destiny is to become a spacefaring species, spreading beyond our home world to other planets, moons, and eventually other star systems. The knowledge we gain from studying the sun will be essential for this endeavor. Understanding how stars behave, how they influence their planetary systems, and how to harness their energy will be critical for any civilization that hopes to thrive among the stars. In this sense, the study of the sun is not just about understanding the past or predicting the future. It is about preparing for the next great chapter in the human story. The sun has been our companion throughout our history, guiding our ancestors, shaping our cultures, and driving our scientific progress. As we stand on the threshold of becoming a spacefaring civilization, the sun remains our guiding light, illuminating the path forward. The sun teaches us humility, showing us that we are part of a vast and ancient cosmos where stars are born, live, and die in cycles that span billions of years. It teaches us resilience, demonstrating that stability and change are not opposites, but partners in the ongoing evolution of the universe. And it teaches us hope, reminding us that even as our own star will one day fade, the cycle of creation and destruction ensures that the cosmos will continue to evolve, giving rise to new wonders we can scarcely imagine. In our time, we have the privilege and responsibility to study the sun with tools and techniques that would have seemed like magic to our ancestors. We send spacecraft to touch its corona, we peer into its interior using the music of its vibrations, and we capture neutrinos that have traveled straight from its core. We build computer models that simulate the churning of its plasma and the twisting of its magnetic fields. And with each new discovery, we come closer to understanding the star that has shaped our existence. Yet, even as our knowledge grows, the sun retains its sense of mystery and wonder. Standing beneath a clear sky and feeling the warmth of sunlight on your face, you are experiencing the culmination of a journey that began deep in the sun's core hundreds of thousands of years ago. That photon that warms you has traveled through layers of plasma hotter than any earthly fire, has been absorbed and re-emitted countless times, has convected upward in churning currents, and has finally escaped into space to cross the void and reach you. In that moment, you are connected to the sun in a way that is both physical and profound. You are part of the same system, bound by the same laws of physics, sharing the same cosmic heritage. The sun is not a distant object to be studied in detachment. It is the source of your existence, the giver of life, the center of your world. As we conclude this exploration of our nearest star, let us remember that the story of the sun is also our story. It is a story of origins and evolution, of violence and stability, of mystery and understanding. It is a story that stretches back billions of years and will continue billions of years into the future. And it is a story that we are privileged to witness and to help tell. The sun will rise again tomorrow, as it has every day for billions of years, bathing the earth in light and warmth. It will continue to shine, steadily and reliably, for billions of years more. And as long as there are beings on earth to look up at the sky, the sun will inspire awe, curiosity, and wonder. So the next time you watch a sunrise or a sunset, take a moment to appreciate the incredible journey of the light you are seeing. Think of the nuclear furnace deep in the sun's core, the tortuous path through the solar interior, the eruptions and cycles that shape the sun's behavior, and the vast distances that light must travel to reach your eyes. Think of the billions of years of cosmic history that led to this moment, and the billions of years yet to come. And remember that you are not just an observer of the sun, but a participant in the grand cosmic dance that it leads. You are made of elements forged in ancient stars, warmed by a star that will one day seed future generations, living on a planet whose entire existence is a gift from the Sunday. The sun is more than just a star. It is our past, our present, and in many ways our future. It is the reason we are here and the key to understanding our place in the cosmos. And as we continue to explore, to learn, and to push the boundaries of our knowledge, the sun will remain at the center of our story, just as it has always been. If you enjoyed this video, there's another one you should definitely watch. It's a great one, diving even deeper into the mysteries of our cosmic neighborhood. And with that, we'll see you in the next video.